Hello viewers and welcome to this new video in my STM32 tutorial series of videos. If you remember a few videos back, I was playing around with the pulse width modulation PWM to regulate LED intensity, and I added a few more LEDs, so I ended up with 4 LEDs running with pulse width modulation. And it basically, as usual, I have created a new project called STM32 World PWM3, and it currently runs like this. Let me show you the output. It's here. So basically, the LEDs run in pairs, 2 and 2, and the way that is done in the code is that in the main loop, I am changing the value with the PWM value, and it goes up and down and up and down and up and down. But this could be handled a bit more elegantly, and in this video, that is what we are going to look at. So first of all, rather than having these linear, it becomes like a triangle wave. Another way of handling this would be to use sine, so-called sine wave. A sine wave is essentially a wave that follows this curve, and the way that is created mathematically is that you are using the sine or cosine functions, and you are having what is known in math as a unit circle, and you have an angle, and based on that angle you will get these values. The benefit visually when you're pulsing a LED is that it slows down around. You don't get those sharp peaks, so it actually visually looks better. Now I'm not even going to attempt to try to explain why it looks better, but it looks better. You have to believe me. Now, I'm not going to dig into the math too much, but just to explain that the cosine function is this one, the blue one, and it goes from the center is 0 and it goes up to 1 and it goes down to -1. Sine is the red one, and it goes again from 0 to 1 and down to -1. That is just to make you understand the sine value. The last thing I want to say about this is that the frequency of this value, if you look at this animation here, you can see that the angle is running at a fixed angular speed. So you can actually describe the frequency as an angular speed as well. So if you have an angular speed of a full revolution in 1 second, then you will have 1 hertz because you go through the entire sine wave in 1 second. Now, angular speed can then be described. Let's say we take this circle and we divide it into 100 samples. So so each sample is 1/100th of the full circle. That means it's about 3.6 degrees. So in that case, you can actually describe it as a constant that you add to the angle every sample. That way you can describe the speed. So let's start to create this in our code here. So the first we will need to do is we need to include the math library to have the sine and cosine function. So if we include math h, then we will have the sine and cosine functions defined. Next, let's define some defines, so to speak. First of all, how often do we want to do this? And since we are running pretty much everything in milliseconds, we could define a sample delay, how many milliseconds do we want between each sample? And let's do 10. That means that we will get 100 samples every second if you're running with 10. Now, based on that, we can actually calculate the frequency. So if the sample delay is 10, our sample frequency will be 1000, because we are talking milliseconds here, divided by the sample delay. Now, does this make sense? Well, if the sample delay was 1000, then the sample frequency will be 1000 divided by 1000. That is 1 hertz. That is what to be expected. Say we are running a sample delay of 2000, then the sample frequency will be 1000 divided by 2000. That's half. So, let's say we are running a sample delay of 10, our maximum frequency will then be 1000 divided by 10, which is 100. So we can go up to about 100 hertz. Now, pulsing a LED at 100 hertz, you wouldn't be able to see it. It'll just be a constant color anyway. So this works quite well for us. We also need a few more defines. It would be convenient to know. No, I'm going to show you another way of doing this. Let's go into our STM32 Cube MX, and you can see when we define the timer, you actually set down here, you have the counter period, which we could call we could call that a sample range. We have certain amount of we have a range where we can define these PWMs, and in our case, now it is possible in STM32 to add user constants. So if we add here, we can add we could call it sample range, and our sample range, we would define that as 1000. Now we have a sample range define, and these defines are available everywhere. So in our parameter settings, rather than having a number here, we could take our sample range minus 1999, because that's how it works in here. Project generate code. So now we actually have a sample range, but if you remember from what I showed before, the sine and cosine functions are actually between -1 and +1. So we need to move that up. So when it's 0, it'll be halfway. So what we can do in here, we can define a sample a midpoint, which is our sample range divided by 2. As simple as that. So halfway up, that will be 500 by default. Let's just try to build this project and see that it still builds without errors, and it does. And let's try to run it and see the output here. So it is still running as we expected. Another thing I want to show is, just to keep in mind, we have this tick counter that counts every second and show the current number of seconds and how many idle loop counts we had. So the higher that value is, the last value, which is currently 18.5 million roughly, the higher it is, the less the CPU is doing. And we can see if that number goes down, it's because we're wasting time somewhere else. Now, let's go back to this and start to add a bit of, let's see, I have of course cheated a little bit. So rather than doing this changing stuff we are doing in here, let's comment that out and let's start some new, and we want a new counter here which we could call next. Oh, sorry, next sample. And if we want to run at, oh, sorry, I'm getting ahead of myself. We need a little bit more. So sorry about that. As I mentioned a couple of times, I am doing this. I'm doing this unscripted. So, but I have tried it before. We also need some variables. Now we have made these defines, but we need some variables to keep track of the different things. First of all, you can see when we are setting the PWM value, we are adding these timer channel constants. So if we want to loop through these, it would be convenient for us to have an array of LED channels. We don't have to define and set that to timer channel 1, timer channel 2, timer channel 3, and timer channel 4. That way we can just loop through these and we can have one statement. It will be convenient later. We also need to keep track of the current angle. So we can do another, and that should not be UN, that should be float values. Float angles equals, and we have 4 values, so we could say 0, 0, 0, 0. We have 4 angles. And then angle changes. That relates directly to the frequency. We can later add a function to do those calculations. But let's just create some for some. If we want to run at 1 hertz, that is 1 hertz, and each full cycle 2 multiplied by m pi, that is a full circle, divided by our sample frequency. That is the calculation of that, and we can do 4 of those as well. Now you'll notice I start with 1. If we could say, okay, this is 2, and we can say this one is 0.5. Remember, we're using floats here, and we could have this one at 0.1. Then we have angle changes of 4 different frequencies. We start with 0, but they're running at 4 different frequencies. Okay, now we go back to this. So we are going to have where are we here? We're going to have a next sample. Now remember, we created those defines, so we actually have our sample delay. So we're running every sample delay milliseconds. Now we can add a if statement down here. If now is greater or equals our next sample, we are going to, and then we are going to say next sample equals now plus sample delay. So now this bit is going to be executed every sample delay milliseconds, and we can do the calculation of our angles in here. Now remember, we have 4 LEDs, so we could start with a for loop that goes from 0 to, let's calculate it just in case we had more, size of angles divided by size of angles 0. That is the usual way to calculate a size of an array. plus plus I. So this will cycle through. What is wrong? We are missing a, no, size of angles. There is, or NE, size of angle, size of angle. Oh, here, we are missing a, there, right? That should, it should still build. Let's just verify that it does. No, there is still something. What am I missing here? I have one too many there, don't I? Yes. Uh, Now I'm getting annoyed. For in I equals 0, I, oh, less than angle of, there we go. It's got to be a statement. There we go. So each time we will loop through this 4 times because our angles area is 4 values. Then we need to calculate, and the calculation becomes really simple because our angles I will be angle I plus angle changes I. There. So that will change the angle. Now we have to do one little check here because if we keep adding, we will go way past the 2 pi full angle. So if our angles I at any times become greater than or equals 2 times m pi, 2 pi, then we want to set this angles I, we will subtract minus equal 2 times m pi. So that will subtract 2 pi's every time it does a full circle. Now we can basically do the same thing we are doing up here. Let's steal that line. We use the help sim set compare, and rather than doing hard-coded sim channel, we do what did we call it? Let's go up and look. We call it LED channels. So it will be LED channels I, and rather than setting it this, we will set it at angles. No, we need to calculate. Actually, should we calculate that separately? I think that will look better. It's not strictly necessary, but we need an let's do it in here. It's not really. So basically, how do we calculate the PWM value from an angle? Well, we need to start with our sample midpoint, so 500, and remember it can go between 1 and -1. So we need to subtract another value that is based on our sample midpoint again, multiplied by sinus of sine of our angles I. That should actually do the trick. This one will go between -1 and 1. Multiply that by that and subtract it from the sample midpoint. And that's pretty much it. Let's try to build this and see how it runs. And execute. And let me show you the output. There we go. So now you'll see that Okay, the oscilloscope is actually showing the change of the red LED because it's only looking at timer channel 1. But you can see they run at different frequencies. The red LED, what do we have up here, is running at 1 hertz, so it should pulse roughly, no, very precisely, once every second. And the green LED is running at 2 hertz, so that pulses twice every second. And is that a blue LED? Device part. The blue LED is running at, oh, this is what I want. This is what I wanted to do. Is running at half a hertz and, 1.11. That is a silly value. Let's try to do this. And let's try to maybe 2.5. Doesn't matter. Let's run it a bit faster. So there you go. So now we have 4 individual channels that are being handled at 4 different frequencies and can pulse individually from each other, running still from one timer. Now there is one more improvement I like to make with this. We are running these calculations down in our main loop, but if we look in the STM32 Cube IDE, it is actually possible to enable a global timer interrupt. Let's try to enable that. And then rather than running it in the main loop, have this one being interrupt driven. So we look down here, if we add, where do we do this? Up where we start the PWM channels, we could actually start an interrupt on one of the channels. We don't need to interrupt every channel. We will leave the rest as it is for now, but let's do a interrupt callback. And when we are using PWM, the callback is called pulse finished callback. So every time a pulse is finished, this callback, and we can check as usual if our HTIM instance is TIM4, then we will, in order just to see that this works, I just want to add, we can do that here. We can add a callback counter, which start with 0. And at the moment, all I want to do is increase the callback counter. And then let's print that out down in here. So we have loop equals 1000. Wait a minute, let's remove this. It might be in the way. I'm not very good at doing that. We do a callback, also LU, and then we have CB count. So let's try to run that. But let's show our serial output here. So now we get actually 100 times, and remember 100 times every second, and remember that that is our frequency. So rather than doing this calculation down in our main loop, we could, let me copy that. I need this. No, I don't need that. I need this. And then I need to, that we could do this calculation up in our callback instead. So where are we here? We need to basically go to these 4 channels and do this calculation and set this. So now it actually runs up in the callback. It doesn't run in our timer. Let's try to see if we can build this build project. We could. Let's try to flash it. And let's start by seeing the output. It's running. And now let's look at how it works. So it works exactly the same. So our only device there, our entire main loop is now reduced to doing nothing except printing that tick every second. So the moment we start the timer channels, everything is handled in the hardware with one exception, and that is every time one of these pulses are finished, this callback is called and it can change the value. You'll notice that we only generate an interrupt in one of the channels, and then in our callback we are updating all our channels. Now, floating point is expensive. It is slow in an embedded programming. So this is a little bit naughty to do this, but if we're looking down at our output, you will see we're still at 18.5 million. So the fact that it's doing this 10 times every second is not really noticeable at all. So that is pretty much all I did, and I think I'm pretty much done with pulse width modulation for now. The next video, I think I'm going to start looking at the UARTs, but unless I get a better idea in the next couple of days. Let's see about that. As usual, I will commit and push this to JIT so you can see it there. Thank you for paying attention. As usual, please like and subscribe, and I love to get comments, so please comment down below if you get this, if you got this far in the video, and tell me what you like about the video and tell me what you didn't like. Have a wonderful day.